Question number one, we're given the endpoints of the diameter of the circle. So I'm just going to draw a little estimate picture. So if I have the coordinates of the endpoints of the diameter, a diameter passes through the center of the circle. So the center of the circle is something that I'm going to need in order to write the equation of the circle. And it's something that I'm going to need to get in order to find the radius, which is the other thing I need to write the equation of the circle. The equation of a circle is x minus h squared plus y minus k squared is equal to r squared. So the h and k are the coordinates of the center. So we need to find the center to find those. And the radius is r. So we need to find the radius as well. So in order to do that, first I'm going to find the center of the circle, which is the midpoint of the diameter. It's in the middle of the two endpoints of the diameter. So midpoint formula is x1 plus x2 over 2, the average of the x coordinates, comma, the average of the y coordinates. So that would be 0 over 2, negative 2 over 2, which is 0, negative 1. So that would be the center of our circle. And now we just need the radius. To find the radius, you can either find the length of the diameter and divide by 2, but if it doesn't work out nicely, and in this example it doesn't working out nicely, but if it doesn't work out nicely and you have like a radical as your length, that could get a little bit messy, but when you're dividing a radical by 2. So I'm just going to find the length of the radius right away. I'm going to use the center that we just found, and I'm going to use one of the endpoints of the diameter. I'll just use the first one I see here, A. Let's pretend this is A. And if I find the length using the distance formula from the center to that endpoint, that would be the radius of the circle. So I'm going to go to my distance formula, and I'm using the center, which is 0, negative 1, and I'm using point A. So I have my x coordinate minus my other x coordinate, my y coordinate minus my other y coordinate. So that would be negative 4 squared plus 3 squared. That is 16. Oops, I wrote to the ninth power. That was 3 squared. That's 16 plus 9, which is radical 25. And radical 25 is 5. So that is the length of the radius. So now we just need to rewrite the equation of the circle using the center and the radius that we just found. So we have x minus the x coordinate of the center, which is 0, y minus the y coordinate of the center, which is negative 1, equals to r squared. And yes, you can just write that as 25. And that would be our equation of the circle. X squared plus y plus 1 squared equals to 25. Taking a look at number 2, we need to figure out which step the error was made in. So in step 1, the only difference from the original equation to step number 1 is that the negative was distributed, and that was done correctly. So the error is not in step number 1. Now let's take a look what happened in step number 2. It looks like Kevin started completing the square and found the C value that completes the square for the x terms, and also added it up, put it on the other side as well. So we have a couple of issues here in step number 2. Number 1, Kevin is completing the square and adding 4 to the side, but he's subtracting 4 from this side. Remember, we need to keep our equation balanced. So whatever we do to the left-hand side, we also need to do to the right-hand side. So if Kevin found that the number that completes the square is 4, then he should also be adding 4 to this side. So step 2 is the error. Instead of doing two different signs on both sides of the equal sign, whatever Kevin is doing to the left, he should also be doing to the right. He should be adding 4 to both sides. Okay, moving down to number 3. So right now, this equation is not in the format where I can clearly see the center and the radius. So I'm going to have to put it into that format. So first, I'm going to get everything to the other side except for the constant. So x squared. And I'm going to subtract the 8x to the other side. So when it moves over the equal sign, it becomes the opposite sign. And I am going to be completing the square, so I'm going to put a little box here. And then my y terms. And I'm going to move the negative 6y over so it could be with the other y terms. So it's going to go from being negative to being positive. And I'm going to put my little box here because I'm going to be completing the square. And I'm going to keep the constant where it is on the right-hand side of the equal sign. But remember, whatever I do to the left, I also have to do to the right, unlike Kevin in number 2. So I'm going to put my boxes to indicate that whatever I put here and here, I'm also going to have to put here and here. Remember, we find our number that goes in the box using the formula C equals to B over 2 squared. So for our x terms, our B is negative 8. So we have negative 8 over 2 squared. And remember, when we factor, since we're completing the square, it's going to factor to the same number written twice. And the trick for figuring out what it factors to without actually doing any factoring is it's going to be whatever your b over 2 is before you square it. So our b over 2 is negative 8 divided by 2, which is negative 4. So that's what it's going to factor to. Negative 4 squared is 16. So 16 is the number that completes the square. Let's do the same thing for the y coordinates. 6 is our b coefficient. So that would be 6 over 2 squared. Just like with the x coordinates, this is going to factor to something repeated twice because we completed the square. And it's going to be what our b over 2 is before we square it. So here, 6 over 2 is going to be positive 3. And 3 squared is just 9. Now, I'm just going to add up what is on the right-hand side of the equal sign. So that would be 39 plus 16 plus 9. And that is equal to 64. Now, all we have to do is figure out what the coordinates of the center and the radius are. So our center is going to be 4, negative 3. Remember opposite signs from what you see in the equation, because our general format for the equation of the circle has a minus. So if you're seeing a plus, that means that the original was a minus because a minus minus makes a plus. Okay, and this is r squared. So r would be radical 64, which is 8. So here we have our center and our radius. Okay, circumference is 2 pi r, and this formula is given to you on the Regents exam. So we'll give it to you on the test, on the quiz. So the circumference is 10 pi. Let's find the radius because we're going to need the radius in order to find the area. So to get the radius by itself, we're going to divide both sides by 2 pi. That's going to cancel out. And since I have a pi on the top and the bottom, that cancels out. 10 divided by 2 is just 5. So now I can find my area of the circle, which is pi r squared. So that would be pi 5 squared, which is 25 pi. Moving on to number 5, we have a rectangle. So we know a rectangle has 90-degree angles. So we have right triangles here. And we need to find the perimeter of the rectangle to the nearest tenth. So it's okay if we get a decimal because it does want us to round. So that means trig is an option. And this is a review question. This is not on the circles unit. So I want to find this and I want to find this. So I'm just going to label them two different things. So if I focus on the 30-degree angle, this side would be opposite, this side would be adjacent, and this side would be the hypotenuse. Let's find x first. So I'm going to write here ka toa. So to find x, I'm looking for adjacent, and I have hypotenuse. So that would be cosine. Cosine of the 30-degree angle equals to adjacent over hypotenuse. Let's put this over 1 and cross multiply. 12 cosine 30 is equal to x. And if I type this into my calculator, 12 cosine 30 is approximately 10.392. So x, I'm going to get rid of x, is approximately 10.392. And rectangles have opposite congruent sides, so is that. Okay, now to find y. So y is opposite from the 30-degree angle, and we have the hypotenuse, so we're going to use sine. Sine of the 30-degree angle is equal to opposite over hypotenuse. Put this over 1 and cross multiply. 12 sine 30 equals to y. So 12 sine 30, enter, and that is 6. So here I have a 6, and here I have a 6. So let me put these into my calculator. So that's 10.392 times 2, and 6 and 6 is 12. So let me add 12 to that. So the perimeter, when you add all the sides together to the nearest 10, should be approximately 32.8. Now, if the question said exact value, trig wouldn't be an option because then you would expect your answer to be in radical form, not as a decimal. And we know as soon as we hit the cosine and sine button on the calculator, it's going to give us a decimal that goes on forever. So if it did say exact value instead, then what you would need to do is you would need to use 30, 60, 90 triangle ratios. It's actually pretty easy to use those, so I'll just go over here right now. Remember that the ratio for 30, 60, 90 triangles is 1 to radical 3 to 2. So you want to find the small side. Right now, you have the largest side across from the largest angle. So you have the 2 part of the ratio is 12. If we want to go back to the smallest side, we're going to be dividing, and we're going to be dividing by 2. So the smallest side is going to be 6 across from the 30-degree angle, just like we found over here. Now, if you have the smallest side, it's pretty simple to get to the middle biggest side, which is the side across from the 60-degree angle. You just take your smallest and multiply it by radical 3. So that would be 6 radical 3. And then, since it does want you to round, in your calculator, you can type in 6 radical 3 plus 6 radical 3 plus 6, and you should get approximately 32.8 as well. Okay, number 6. I have vertical angles. I know that for sure. And I know that angle A is an inscribed angle that opens up to arc CD. And I see that angle B is also an inscribed angle that opens up to arc CD as well. Since these are inscribed angles that intercept the same arc, they have to be congruent to each other. C is also an inscribed angle. And notice how it opens up to arc AB. D is an inscribed angle, and it also opens up to arc AB. So angle C and angle D have to be congruent to each other because they're inscribed angles that also intercept the same arc. Be careful. Some people were saying the alternate interior angles were congruent. You don't have any parallel lines here. We can't just assume that. Looking at the answer choices, this is all I can conclude. I don't know anything about the chords or the arcs here, so this is literally all I can conclude. So I don't know this because I don't have one of our 5 methods of proving triangles congruent. I do know this because I do have AA. In fact, I have AAA. This is not true. This would be true if we had parallel lines, then we would have congruent alternate interior angles. But that's not true here. And we have no reason to believe that arc CA and DB would be congruent. We don't know anything about chord CA and DB. That would be true if these chords were congruent to each other. The only one we can say for certain is 2. Okay, moving along. So what I'm going to do is I'm going to represent the arcs and their ratios. So DF would be 5x, FE would be 2x, EG would be 1x, and GD would be 7x. And I know that altogether, all the arcs of a circle have to combine to make 360. So I have here 15x is equal to 360. I'm going to do 360 divided by 15 on my calculator, and I got x is equal to 24. So now what I can do is I can plug in and I can find the arc measurements. But I don't really need to in order to answer the question, because all it's asking for is a pair of inscribed angles that are congruent to each other. Oh, it also wants their measures, so I am going to have to plug in. Let me do that. 7 times 24 is 168. So this is 168 degrees. 24 times 5 is 120 degrees. 48 degrees and 24 degrees. So I see that angle F opens up to arc DG, and I see that angle E also opens up to arc DG. So these are 2 inscribed angles. They're vertexes on the circle. They're 2 inscribed angles that intercept the same arc DG. So they do have to be congruent to each other. And since they both intercept arc DG is 168 degrees. 168 degrees divided by 2 would be 84. So both of these angle measurements over here would be 84 degrees. As inscribed angles are half the measurement of their intercepted arcs. Not the only pair of congruent inscribed angles here, but it only asks for one example. Okay, moving along, I know that I have a circle, and I know that A, B, C, and D are located on the circle and that they form a trapezoid. I'm a really bad artist. Oops. Let me retry that picture. I'm going to try to draw the trapezoid first and then draw the circle around it because I'm a terrible artist. A, B, C, D. That doesn't look much better, but that's okay. We get the idea. And it tells us that AB is parallel to CD. Which statement must be true? A lot of people automatically were going with arc AB congruent to arc DC. That's not true. That would be true if AB and DC were congruent, because congruent chords intercept congruent arcs. But they're not congruent, they're parallel according to the givens. And our theorem for parallel chords is that parallel chords, the arcs formed by them in between them that they intercept are going to be congruent. So here, oops, I went too far with that. Here is the arc that's in between those two parallel chords on that side. And this is the arc that's in between the two parallel chords on this side. So that's AD and BC. So that would be answer choice number 2. Moving along, we have a diameter, and the diameter is perpendicular to chord CD. If we have a diameter that's perpendicular to a chord, it actually bisects the chord, which means cuts it in half. So if the whole length of CD is 7, if the whole length of that chord, if the whole length of that chord is 14 and it's being bisected, that means each piece is going to be 7. So CE is 7. Let's take a look at the next one. It says explain why arc AD is congruent to arc BE. Let me make this one a little bit bigger so that you guys can see it a little better what I'm talking about. Okay, so we need to explain why these two arcs are congruent. So what I see here is I see congruent radii because all radii of a circle are congruent to each other. So that means that I have two isosceles triangles here. And when I have an isosceles triangle, not only are two sides congruent, but the angles opposite those sides are also congruent. And all of these angles are inscribed angles. This angle and this angle are central angles. If these two angles are congruent in both of the triangles, so let's say these are, for example, 50. 50 and 50 make 100. These angles would have no choice but to be 80 degrees. So since all the other angles in the triangles are the same, these central angles have to be the same as well. And since these are congruent central angles, the arcs that they intercept need to be congruent as well. Let's find the value of x. 15x minus 40 is equal to 10x plus 10. 15x minus 50 is equal to 10x. Negative 50 is equal to negative 5x. I just subtracted the 15 to the other side. And then if I divide everything by negative 5, I have 10 is equal to x. So our x value is 10. Now I can find the measurement of arc AD. That's 150 minus 40, that's 110 degrees. And arc BE should be the same measurement. And it is. It is 110 degrees. Now I can find arc BD because I have 110, 110, and 40. Let me add those together. 110 plus 110 plus 40. And I'm going to subtract that, which was 260 from 360. And I'm left over with 100 degrees. Please only be watching 11 and 12 if you have already learned this in class. We are going to be talking about arc length now. So for arc length, you have two options. You can use our part over whole equals to part over whole formula. Remember that one side is about the arc lengths. One side is going to be about the central angle measurements. So we have the pendulum of a clock swings through an angle of 2.5 radians. So it's important to realize that our question's in radians here. And it travels through an arc of 50 centimeters. We need to find the length of the pendulum. So let me draw a picture. So the angle is 2.5 radians. The arc is 50 centimeters. So we're looking for the length of the pendulum. So we're basically looking for the radius. We have the central angle, we have the arc length, and we're finding the radius. So on our side over here, that's going to be about arc length. The arc length of this section of the circle is 50 centimeters. We already know that. And the arc length of an entire circle, we're basically talking about circumference when we're talking about all the way around on the circle. And remember, circumference is 2 pi r. I don't know what r is yet. I need to solve for it. So I'm just going to leave 2 pi r over here because that's going to be the arc length, the circumference of this entire circle. Now, for the other side of my proportion, we're going to be talking about the central angles. So since our central angle here is in radians, all of the central angles add up to 360 degrees in a circle, but we need to use that in radians. So if you convert 360 to radians by multiplying by pi over 180, we get 2 pi as our conversion. From here, we can cross multiply. So I have 100 pi is equal to, what's 2.5 times 2? That is 5 pi r. I want to get the radius by itself. So I'm going to divide both sides by 5 pi to cancel it out. And notice how I have a pi in the numerator and the denominator, so that cancels out. And I'm left with 20 for the radius. Now, since our angle was in radians to begin with, we also have another option. We could have used our arc length formula, s equals to r times theta. And remember, this formula can only be used if your central angle is in radians. If it's in degrees, this is not an option. So our arc length was 50. We were looking for our radius, and our central angle was 2.5. So all you would need to do is divide both sides by 2.5, and you get the same thing, that r is equal to 20. So I showed that both ways, but if your angle is already in radians, it's just easier to use the formula s equals r times theta. Arc length equals to radians times to radius times the central angle in radians. But remember, this formula can only be used when your angle's in radians. Okay, moving over here. We have two concentric circles with center O, and we have radii OC, OD, OGE, and ODF are drawn. If OC is 4 and OE is 6, which relationship between the length of arc EF, so it's this arc length question, and the length of arc CD is always true? The length of EF is 2 units longer than the length of arc CD, 4 units longer. I don't know. let's make up an example because I can't see what's going on here. Let's make up an example. Let's say that our angle here, and I'm just going to keep degrees here because often we like working with degrees. So I'm going to say that our angle here is 60 degrees, and I just made that up. But I just want to test out an example so that way we can see what the relationship is. So I'm going to find the arc length of CD using this made up angle. I'm going to find the arc length of EF using this made up angle, and then I can compare them. So I'm going to use my proportion. So the arc length of, I guess I'll start with EF because I'm using green. I don't know what the arc length of EF is. That's what I'm trying to find. Over the circumference of the circle, because the whole way around the circle, the whole arc length would be the circumference. So that's 2 pi r. The radius is 4. So that's 4 times 2 is 8 pi. And then we have the central angle over all of the central angles together. So that's 360x is equal to 8 times 60 is 480. And then if I divide by 360, and I'm going to just multiply by pi as well, because I want to be able to compare the numbers, I got approximately 4.189. Okay, let me find the arc length for the smaller arc. So arc length, oh, my bad. See, I'm always messing up. So when I found the, what do you call it? The circumference, I was accidentally using the radius of the smaller circle. But we were talking about arc EF, which is an arc of the larger circle. So I should have been using the radius of the larger circle, which was 6. So that is going to change my answer. So that would be 2 pi 6, 2 pi r, 2 pi 6. So that would be 12 pi. So that's going to change my numbers a bit. Let me redo that really quick. 12 times 60 is 720. So I'm going to divide 720 by 360. And that was 2 pi. And if I put 2 pi into my calculator, just in case I need that, that's approximately 6.283. Okay. 2 pi r, and this time I'm using 4. That's the radius of the smaller circle. So that would be 8 pi. And then the central angle over 360 degrees. So that would be 360x is equal to 60 times 8 is 480 pi. And then let's divide that by 360. And I'm also going to multiply by pi. And I got that this is approximately 4.1. 4.189 approximately. So it appears so I'm actually going to go back to the exact values to make it easier to see, because right now it's not super easy to see. So our exact value here was 2 pi, and our exact value here is 480 over 360 pi. It doesn't work out evenly. In your calculator, type in 2 pi in the fraction button, divided by, oh, sorry, not 2 pi, just the 2. Oops, my bad. Just the 2, just the coefficient, divide it by 480 over 360. And you should get 1.5. So the relationship between these two is this one is 1.5 times as large as this one. That one was a lot of work. The last part of this video are the two proofs on the review sheet. So I see from the proof statement that we're proving a proportion. And before we can prove a proportion, we need to prove that the two triangles are similar to each other. Now, the proof statement is going to tell us which two triangles we're focusing on. So CT, CH, those are two sides of this big triangle. TO and TH, those are two sides of this small triangle. So those are the two triangles we need to prove similar. Triangle CTH and triangle TOH. So since this one is inside of this one, first I'm going to look for what's shared. And if I'm proving triangle similar, I'm looking for angles because I want AA. And I see that angle H is not only in the small green triangle, but it's also an angle of the big purple triangle. Now, the next thing I notice is that from the givens, because the givens are always there for a reason, we're told that T is the midpoint of arc CH. That means that arc CH is being split into two equal parts by the midpoint. And I know that the whole arc CH, since segment CH is a diameter, I know the whole arc CH measures 180 degrees, as does the other side, arc CH. And since it's being split equally, that means each half is 90 degrees. And guess what? This angle right over here is a central angle. Its vertex is on the center of the circle. And central angles are equal to their intercepted arcs. So if the arc it's opening up to, TH, is 90 degrees, angle THO is going to be a 90-degree angle as well. Now, I just need to find a 90-degree angle in the big triangle. And it looks like it's going to be this one, so let's figure out why. This angle, angle T, or CTH, this angle right here, is an inscribed angle. Its vertex is on the circle. And it's opening up to, it's intercepting arc CH, which is 180 degrees. And inscribed angles are half their intercepted arcs. So if the intercepted arc is 180, half of that would be 90 degrees. And that's all we need to prove the triangle similar. Now, as long as we mention that those two angles, two pairs of angles, the right angles and the shared angles, are congruent, we have AA for proving the triangle similar, and then there'll be one more step to prove our proportion. I'm going to pause the video and write it up, so that way you can see it written up. Please pause the video as well and try to write it up yourself if you haven't already. This is a very, very, very complete proof. Please pause the video and check it out. It took me a lot of steps to explain why we had right angles. After that, it was just proving the triangle similar by AA, and one more step to prove the proportion, due to the fact that corresponding sides are similar triangles are proportional. Remember, anytime you prove a proportion, it's the same reason every time. Corresponding sides of similar triangles are proportional. Let's take a look at the last proof. Looking at the proof statement, here's BE and here's CE. This triangle has BE as a side, and this triangle has CE as a side. So those are the two triangles I'm going to want to prove congruent because those have BE and CE as sides. And after I prove them congruent, then I can see BCDC, BE, and CE. So that's kind of my plan. Already, I see vertical angles. That might be helpful. I also know from my givens, AD is parallel to BC. And remember, if I have parallel chords, then the arcs in between them, so this arc and this arc, are congruent to each other. And remember, chords that intercept congruent arcs are congruent. So that would make AB and CD congruent to each other. Lastly, notice how angle A is an inscribed angle that opens up to arc BC. And notice how angle D is an inscribed angle that also opens up to arc BC. So those have to be congruent because inscribed angles that intercept the same arc are congruent. And now we have AAS. After that, it is one more step to prove the triangle's congruent. This one's not going to be as long to write up as the first one. Let me pause the video and write it up. And there we have it. Oh, I forgot a step. Technically, before I can use a theorem about inscribed angles, I should state that these two angles are inscribed angles. So I'm going to add that as step 4.5. I'm just going to add that. Angle BAE and angle CDE are inscribed angles. And I know that because angles with their vertex on the circle are inscribed angles. Please pause the video so that way you can take a look through this proof.